Okay, good morning. We're going to continue talking about profile and M-foil. So today is lecture 17. Oh, lecture 18, right, today? Okay. Before we start, any questions on the homework 3, the symmetric airfoil design? So you should try to start early. It's pretty straightforward. You can actually finish it pretty quickly, but there is a possibility you might get confused with something. Yes. I believe I answered this yesterday. So get it, if you get the T over C max to within 0.5% chord, that should be good. So in other words, example is, let's say you have 11% chord, T over C, 11.5, 12, something like 12.5, something like that. If one of these is the minimum, then that's fine, that's enough. You don't have to go any finer than that. Okay, any other questions? Okay. So in the last class we were talking about how to install the profile code and the M-foil code. And so when you unzip the file that I gave you, you'll have these directories extracting. So this is a parent directory, and then you'll have work, bind, M-files and runs. And we talked about install the M-file parent directory. I don't know if this still needs to be done, but this is just like if something doesn't work, this might be the problem. So install it in a parent directory where there is no space. Okay, so that's kind of where we stopped. We'll resume from there. So this M-foil is going to take a little while to get used to. So hopefully by kind of doing a combination of writing down some steps here and doing some demos, it'll become clearer. So first, when you want to start M-foil, so remember M-foil is the MATLAB interface, right? It goes and runs profile whenever you ask it to go run a profile file. So you have to open MATLAB. And change directory is simply folder, same as folder. change the directory to mfoil, which is the parent directory /m_files. Once you're there, in the MATLAB prompt, you'll have this double caret kind of thing. If you type mfoil, it'll open up an airfoil selection. I don't know what it's called, like a window. It'll say select the airfoil, right? Then you select the airfoil. The meaning of select the airfoil means select the profoil input file. So this input file has the complete definition of the airfoil in a way that the Profoil Fortran code, the design code, understands. So when you select this input file, Profoil will run this and then it will design the airfoil and it will plot it, right? That's what is the meaning of select airfoil. And you select this airfoil from the runs directory. So in mfoil, there is a runs directory, and this is just a way to keep things organized. That's the idea behind it. And in runs, you might have various subfolders like project 1, project 2, or whatever. Reflexed wing, something or the other, UAV wing. Let's say you're designing a wing for some UAV project. You could have all these kind of folders, and project 1 might have, like this might be your real project 1, right? You might have various attempts. So you might have something called try 1 or attempt 1 or something like that. It's just your own bookkeeping. You might have various folders. And these .in files are the input files for Profoil. You can call them anything, but I usually call them as .in because they are input files for Profoil. Like that, the UAV wing might have, your own files. You may have files called UAV. So today is 10/19, right? So I have numbering schemes that help me keep track of things. So sometimes when I work on projects, like I worked on the Cirrus jet airplane wing design, the airfoil design for that. And I do these things over many months. And there's a lot of iteration. You design something, it looks good, you send it to them. They do a lot of whatever, CFD, they put structure inside, and then they say, oh, we want a little more thickness, little less thickness. And sometimes when you design a wing, you're designing one airfoil for the root, one airfoil for the tip, maybe something for midsection. So bookkeeping is really important. So you create folders that make sense for you, and this is how I try to keep the thing straight. So I usually number it with something like UAV 2017 October 19th A, because in a given day I might design 10 airfoils or something. And designing an airfoil doesn't mean it's usually a long, laborious task. I might take this and change one number and run the code again, and that's a new design. That's what I call a new design, right? Those are all candidates. After doing 100 of these, we might take the last one and say, this is the best we can do, and go with it. But sometimes you go through 4 or 5 iterations, and then you say, well, this is just I don't like this at all. I want to go back to where I was, 5 steps back. And then if you have all these things numbered properly, then you can go back. Okay, so you might already have a directory structure like this. You might have all these airfoils saved, and when you want to select an airfoil, you'll just go here and say, okay, this is the airfoil I want to load right now. And you click that and it'll load up. Now, what it does is, mfoil will actually copy this to something else. So the way I wrote this, these are kind of archives. I don't want to really touch these. I don't want to go and modify these, right? If I modify it, I would save it under a new name. So when mfoil runs, I don't want to accidentally overwrite these things. So when you select this, what mfoil will do is mfoil will copy. So let's say you select this. I'm going to put a check mark there to say that's what you're selecting. We'll copy this UAV 2017-1019A.in. I know it seems a little laborious to have such long names, but this is just my system. You can kind of do something else. What it'll do is it'll take this and it'll copy it to work. So inside mfoil there's a work directory, right? So let's say mfoil work slash profoil.in. So this work is the working directory. That's where any change you make all changes you make will be happening in the work directory. You're kind of working there. It's like your sandbox. You're messing around there. And then anytime you like something, you save it, and it'll save it into this runs directory with a name that you want. So mfoil will actually copy everything to this. And then mfoil will execute profoil.exe. This is the actual code, right? It'll run the code. When profoil runs, it automatically goes and reads this file. That is because that is the input file for the airfoil. It'll actually read it from work. So work/profoil.in. And then it'll create some output files. So profoil will create output files. In work. Okay, let's talk about the input and output files for profoil. So the input file is only one. So input file for profoil is always work/profoil.in. And there are 3 important output files. These are the only ones we'll really be dealing with. There are other files, but they're not so important. So these will all get written out in the work directory. So profoil.xy, and this has the xy coordinates, which is really the geometry of the airfoil. And then profoil.dump. This will have the converged data, and we'll talk about this more as we go forward. And then you also have the velocity distribution. So this is what the Fortran code does. The Fortran code will read this. It'll run the whole design method, conformal mapping, and all the complicated stuff. And then when it's finished, it'll write out the files. It'll write out the XY coordinates, it'll write out the converged data and the velocity distribution. And mfoil will now read these. in the two figure windows. Right, so these were the two windows we saw last time. The first window is geometry and velocity distribution. That's the top window, and the bottom window is alpha star distributions. So in the demo in the last class, we kind of, you might have seen this window, but we didn't pay attention to it. We were focusing only on this window. But as we go forward, we'll talk about this one also. So, so let's say you have run this airfoil and you want to see how it performs in the viscous world, let's say at some Reynolds number of 3 million or whatever condition you're interested in. Profile cannot do that. Profile is only an inverse design code which can, it'll calculate inviscid velocity distributions for the airfoil that you're designing, but it doesn't do anything with viscous stuff. Because there are really good tools out there for that, and a very good example is Xfoil, right? So now let's say you like this and you want to see how this airfoil performs in under viscous conditions. So if you wish to run Xfoil on this airfoil, you need the coordinates, right? Xfoil will have to read the coordinates. The safe way to do this is to copy this XY coordinate file. You copy the work/profile.xy, right? This file which has got all the coordinates, to some folder where you're doing all the Xfoil runs. I would recommend it be a separate place. For example, that could be under Xfoil runs, you know, where the folder where you put all your Xfoil analysis stuff. And ideally you would do the bookkeeping so that you'll be able to keep track of these things nicely, right? Your profile input file was called UAV 2017-1019A.in, and that's the airfoil that you're running in Xfoil, right? So you would probably copy this into something like UAV 2017-1019A.dat or some, you know, it's up to you. You create your own workflow. This is kind of my workflow. I'm not saying it's perfect, because after some time it gets really tedious to put all these long numbers. But then I often go and look at airfoils from 10 years back as a starting point for some new project. So I find it necessary to do all this. Okay, so now we have got the coordinates. You've copied this coordinate file to something new, and then you can run Xfoil on this. Usually you will have some script file. If you've done this, you know, if this is your very first airfoil, then maybe you'll create a script file that Xfoil will run. Otherwise, you already have a script file. You'll just change the name in the script file and say Xfoil, go run it, and it'll create all the data, right? Then you can look at the polar data, and this all happens very kind of fairly quickly. You just kind of, you're looking at the polar, and then you say, okay, I don't like that, and then you go and change things in Xfoil. You kind of do these 2 or 3 steps, and then you have the polar again. So things like that. So one important thing is, let's say you like this airfoil, or let's say you now go and change some things in the profile input file, right? Let's say you don't like something in the polar and you go change the alpha star here or something. And you run it through Xfoil, you like it, and you want to save that. So you should, if you modify this airfoil, and we'll see this soon. You can modify this in a couple of ways. You can modify either through the MFoil interface, which is through this alpha star distribution. This figure window will go and let you graphically edit things. Sometimes that is easy, and some other times it's just easy to edit the profile.in file, or by editing the profile.in in the work directory, right? This file. And if you modify it and then you like it, then you want to save it. Then remember to save it in runs. So in runs, you will probably go let's say you're just working on this, and you'll say, okay, I want to save it under UAV wing, and you'll just call it B, right? So you'll call it under runs, you will go and save it in, and there's in the MFoil interface, you can go and do that. You can go and say save file, and you can give a name for it. So this might be called, for example, 2017-1019B.in. So this is important to do, because if you don't do this, you let's say you're quitting the session, you're closing your laptop or whatever and going home, something, right? The next time you run profile, so this new airfoil is actually, the data is sitting in profile.in. If you don't save it, that's the only place where it is. The next time you load MFoil, let's say some other airfoil, right? Or let's say you load this again. You say, okay, I'm coming back tomorrow, and you load this. This is archived. You load this will get copied to profile.in, which means whatever you did the previous day is gone. So anytime you like an airfoil, save it under some name in work, because that's sort of the archive of all the airfoil designs you're doing. Does that make sense? I think it'll start becoming clearer when you start using the code. And obviously, if you want to run this airfoil in XFoil, you would copy the XY coordinates into that name, right? You will call it UAV 2017 b.dat, so that you have all the coordinate files in one place, and with the same name you have the input files in the other place. Okay, so let's go and see how that's done, and then we'll come back to making some more notes. Okay, so I am using the MATLAB, is this the MATLAB? Yeah, the MATLAB editor. I'm using the MATLAB editor itself to open the files. So let's say I open some in the runs directory. This was the demo. The only problem with using the MATLAB editor is it will always keep looking for MATLAB files, and you have to say no, all files. So let's say we want to open the demo one that we did in the last class, right? Is it going to open it or not? Okay, there it is. So this is the demo one that we opened in the last class, and that's in the editor. So now in the MATLAB, I want to start MFoil. If I type MFoil, nothing will happen. It will say, I don't know what you're talking about. It will say, do you mean MFilt? No, I don't. So anyway, that's because you're in the wrong folder, right? So I want to go to the mfoil folder, which in my case is in downloads, because this is not my PC, so that's where it's saved right now. Mfoil, and remember we have to go to mfiles, right? Mfoil, mfiles. Then you say mfoil, and it'll start up. And then it'll say, okay, load the airfoil. Select an airfoil from one of the directories, and we'll double click on this and double click on this. Now you can see it's like this thing is all from the Fortran code. This is from Profoil. We'll understand some of all this stuff when we go through it. But so it copies this file demo1.in into profoil.in, which is in the working directory. So if you go here, this is mfoil/work/profoil.in. I think it's copied. I don't know if I have to update. No, I think it's already there. It copies it there. It runs Profoil, and the Profoil run screen output will come in the MATLAB window. Right, so this is all from the Fortran code, and then it'll go and read the output files from the Profoil Fortran code, and it'll plot the output files here, this one and this one. So this is the figure which has the geometry here and velocity distributions, and this is the alpha star distribution. You can toggle between upper surface and lower surface, and then you can do some other things that we'll look at shortly. Okay, so the MATLAB working directory is still the work, right? If you do pwd, it will say mfoil work. And if you say directory, the directory might have a lot of other junk too, depending on if you've sometimes, it might have a lot of other things, but this is the input file, right? This is what got copied from demo1.in. So this is the input file, and then it's created these output files. Profoil.xy, profoil.dmp, and profoil.vel. Now let's go and open profoil.xy to see how it looks. So I am in the work directory, and now I say open and say all files here. So profoil.in is what's opened. We'll open profoil.xy. This is just a coordinate list. It starts from the trailing edge, goes along the upper surface, and then now you can see y coordinates have become negative, and then it will go to the lower surface. In this particular airfoil, for some reason it doesn't, this is a very small, this is practically 0. Okay, so this is 1, 0, but there's a very small, tiny round off error. And then let's open profoil.velocity. That will be less intuitive until you kind of figure out what all that means. This is profoil.velocity, and what this is doing is, it is actually, I believe, it goes from 0 to 360. So here the first column is the phi, right? I told you phi goes from 0 to 60, but in this output file it goes from 0 to 360. You will probably never use this output file on your own, like you will never go and process it by hand or anything. I'm just showing you what it is. The interface does all that conversion. So this is phi, and this is the velocity. And we, I think, made it plot at 5 angles of attack. So it will have 5 of those. It will go from 0 to 360, and then it will start again, and it will do it for 5 conditions. So essentially, from that, the MATLAB interface goes and does some more calculations to plot it as x, as velocity in terms of x over c. Okay, So any questions about this? I think once you start using it, you'll get familiar. Okay, now let's go and see how you do more stuff. So let's talk about what is in the profile input file, because that's what you're going to be using a lot of. So which is, this is what profile always reads. In mfile there's a work and then there's profile.in, right? That's the file. Now profile input file is keyword based. So all of you have written programs, computer programs, but the programs that are written, not like small programs for just doing a homework, but something that's very substantial, that's going to be used by a lot of people for research and all that. Keyword based input files are a good way to do that. Even Xfile, for example, is all keyword based, right? You can go to a menu and type any keyword and it'll go and do some action. Like that mfile profile is also, the input file is keyword based. So keywords are there's something called COORD, there's something called foil, there's something called FES, and so on. So as profile runs, it'll look through the input file. When it sees some keyword, it'll go and do something. It'll go run some conformal mapping or something like that. So these keywords tell profile, this is what is the input file. This is the input, or go do something or something like that. So the first keyword is, you'll see this in the file. You'll see coord, COORD, 120. So this keyword tells, this is usually the very beginning of the file. I think it's compulsory. This has got to be there. This means the airfoil will be generated with 121 coordinate points. It's like 120 panels, right? So that's why this is 120. 120 means there are 120 panels, so there will be 121 coordinate points. And so let's say your airfoil is like this. This will be the first point, second point, and so on. And then you'll have all these 120 points, and then this will be again the 121st coordinate point. This is how it will be in the output file. So the output file will have 121 points. You can change this number, but 120 works well, so you can almost all throughout this code, you can leave it alone too. It's just there, just to tell you what it is. That's what I'm writing it here for. And if I go to the PC and look at profile.in, that's the very first line, coord 120. It's there, that's where it's there in all the input files. So let's say I open the symmetric airfoil we're going to do today. That also has this. So all the files will have this as a starting line. Now we're going to start off first with the symmetric airfoil. the airfoil we did the other day was a cambered airfoil, right? But initially we'll start off with a symmetric airfoil. It's kind of easier to understand in some ways. So if you want profile to do a symmetric airfoil, pretty much the next line you put after coord is SYM. That will tell profile you're telling the profile code that you're designing a symmetric airfoil. And that will look like this. So in the symmetric airfoil demo that we'll be looking at soon, you have this line. And then you have these these lines are the ones you will actually work with. These are called foil lines. So these are really important because they tell the code how you want to divide the airfoil into different segments, where you want the segment endpoints, and what are the alpha stars for the segments. So these lines will look like this. You will say foil, and then there will be one number, which is phi. Then there will be another number, which is alpha star. So these are the two required arguments. I'm calling these arguments because for this line these are the two inputs, right? So input arguments. Now the phi is the phi for the segment endpoint. And the alpha star is really the alpha star for that segment. So you have to somehow tell the code that you're dividing the airfoil into so many segments. First segment has got phi of so much, alpha star so much, second segment, third segment, fourth segment, like that. And now, so let's look at an example. So in a 4-segment airfoil, we'll go on the cambered airfoil demo. So it's got foil 14.5, 7, foil 31.0, 7, foil 45.0, 3, foil 63. So this is phi and alpha star for segment 1 and phi and alpha star for segment 2, segment 3, and this is for segment 4. So this is the airfoil that looked kind of like this. In the circle plane, you had segment 1 somewhere here, segment 2 somewhere here, segment 3 somewhere here, and segment 4 somewhere here. Right? So this is one segment endpoint 1, 2, 3, and 4. 4 is always 60. Right? So this is something like this. The airfoil turned out to be something like this. And alpha star for this was 7. This also was 7. This was 3. And this was 3. Right, so this is so the idea is this whole design method is based on taking regions of the airfoil and saying what is the alpha star for that, right? Any alpha higher than that on the upper surface will have adverse gradient, any alpha lower. All that is fine, you can create a method like that, but then you have to have some user-friendly way of putting it into the code, telling the code this is what I'm doing. And this is a nice way to do it, right? This keyword-based method is a good way to do it. So you can have as many, if you have 10 segments, then you'll have 10 foil lines. So Profoil automatically, by looking at the number of foil lines, it'll know, oh, it's a 10 segment airfoil if there are 10 foil lines. Of course, they have to be in order, so don't try to, put 45 before 31, then the code will come out with an error. So now these are the two required arguments. So let's look at the foil line again. Foil, then you have phi, then you have alpha star. And the last phi has to be 60, right? And then you can have some more things. You can have segment number, and you can have some other stuff. So these are required. And these are optional, ignored by Profoil. But sometimes you see these for visually, when you're looking at a file, for visually understanding the phi and alpha star variation. So if you have a really complicated airfoil description, here we have 4, but sometimes you might have 20 or something. So it'll just look like a mess of lines and you don't know what these things mean. Like if you put a segment number after that, then you can go and say, okay, the 11th segment, what is the alpha star? And you can see it. It's instead of sitting and counting there. So I don't know if I have a file like that as an example on this computer. Let's see. No, open. I don't think oh, maybe. Yeah, maybe this one has it. Like, look at this. This is a symmetric airfoil example that I believe I give this as a template for you for project 1. It's got 22 segments, right? So if you want suddenly, for some reason, if you want to know the alpha star of the 18th segment, imagine these things aren't there. Then you'll have to go and count 1, 2, 3, 4, 5, 6, blah, blah, blah. But because this is there, you can go to the 18th segment and say, okay, 18th segment has 3.96 alpha star. So what happens in Profoil is, Profoil only reads these two. I mean, it actually does read this, but don't worry about it. So these are the important things. This part is really just for user friendliness. Okay, so again, you'll start getting familiar with this once you use it. Okay, so looking some more at this cambered airfoil demo. So we saw how okay, so this 4-segment demo that I showed in the last class, it's a cambered airfoil. First segment, second segment, third segment, fourth segment. Now, this particular segment endpoint number 2 is the aerodynamic leading edge. It's not the geometric leading edge, but it's the aerodynamic leading edge. So I don't know what else to call it. I just call it aerodynamic leading edge. So when you create a geometry or an input file in Profile, you have to tell Profile where the aerodynamic leading edge is, which endpoint corresponds to the aerodynamic leading edge. So in the cambered so this so unless the airfoil is a symmetric airfoil, this endpoint 2 will not correspond to 0, 0, right? 0, 0 is the geometric leading edge. So what is the meaning of aerodynamic leading edge? So remember, we have upper surface and lower surface rules, right, for what alpha star means. So this aerodynamic leading edge demarcates is that the correct spelling? Demarcates or divides the airfoil into let's say aerodynamic upper surface and aerodynamic lower surface for the alpha star rules. So just to recap, on the upper surface, aerodynamic upper surface. For any segment other than the first, if alpha z is greater than alpha star, what happens to the velocity gradient? Will it be favorable, adverse? If alpha z equals alpha star, it's going to be 0 gradient, right? If alpha z greater than alpha star, adverse, right? On the upper surface it will be and vice versa. Whereas on the lower surface, which is the aerodynamically lower surface, the rule is opposite. So for any segment other than the last, if alpha z is greater than alpha star, the velocity gradient is going to be favorable. So the method in your airfoil input definition, you have to tell the method at what segment endpoint you want this rule to switch from upper surface to lower surface, because the number of segments can be anything, right? Somehow the profile has to know this is what you want as upper surface segments and this is what you want as lower surface segments. So the keyword or the segment endpoint into the segment endpoint divides the airfoil into aerodynamic upper surface and aerodynamic lower surface for these rules, for this rule switch, let's say. So you have to tell profile that, and the keyword used for that is ILE. So for example, the demo file has the 4 segment demo file has ILE2, which is because we want the segment endpoint 2 to be the aerodynamic leading edge. So here 2 is the aerodynamic leading edge. Okay, so ILE2 tells us that this segment, right, foil 31.7, this endpoint is the aerodynamic leading edge. Okay, then we have Then we have another keyword which is called alpha SP. So this keyword is used to tell profile the number of alpha z values at which the velocity distribution is calculated. Okay, so when you say alpha SP and then there's a number 3, that means you're telling profile I want velocity to be calculated at these 3 alpha z values, and then you have to give the 3 alpha z values immediately. Now something that could be changed in future, but right now it's a little, this is the way it is if you give 3 and if you give only 2 numbers here, then I don't know, I think profile will come out with an error message. It'll expect, if you put 3 here, it'll expect 3 numbers after that. And if 3 numbers are not there, it'll come out with some error message that I don't know if it'll even be clear what it is. We can go run it and see. I mean, this should have, at some point, somebody should actually go and make it so that if you put 3 here and there are only 2 numbers, then mfoil should actually tell you with a nice error message saying, hey, you said 3, but there are only 2 numbers. What do you want me to do? Something like that, right? But I think if I remember correctly, it'll just give some weird error message, so something that needs to be fixed. But so let's go and see how that looks. So in the demo file, I think we have alpha SP5. Can you read this? Yeah. So alpha SP5, that means you want the velocity plotted at 5 alpha z values, and those are the 5, 1, 2, 3, 4, 5 numbers here. So these are the alpha z values at which the plots are made, and that's why there are plots here. This plot here has 5 velocity distributions, upper surface and lower surface. So it starts from 1, 3, 5, 7, 9. Okay, so let me see what happens if I just put 4 numbers. I think it'll, if I remember correctly, this is profile.in, right? So this is what, I can save this, and if I run it here, yeah, this is the kind of error it'll give. It'll say runtime error F6103. This is a Fortran error, right? It's like a Fortran error message. and in read profile dot in invalid real, you just don't know what this means. And then mfoil, because profile crashed, mfoil comes and says, hey, this file is not there. I think the profile run was not successful. I mean, sometime if I get the time for this, I should really go and say something better than this. It should go and say, hey, you've asked me to do five numbers, but only 4 are there, so you have to fix it, right? So just be aware that this can happen. And this is possible when you're quickly changing a lot of things. You go and remove one number here, and then you forget to update this, right? This is easy to do. So let's go back and say 9 now. The mfoil interface hasn't crashed. It just didn't finish running, right? It just said there's some problem. So you can now go and put back that number and run profile, and now it will run correctly. Now if you go here and say it's finished running properly. What happens if you put one more number here? I think it'll just get ignored. Let's put 11. I think it'll just ignore that last one. It might say, I don't know, you have something called 11 here, I don't know what you're talking about, because that's not a keyword, right? It actually ran, I believe. Let's go and see the MATLAB window. It actually ran, but it'll give a warning. You have to scroll up for all these things. It'll say word is not in profile dictionary, or line number 26 is not expected. Line number 26, it's actually talking about this, but somehow it's counting it. I think it's not counting the blank lines. So in the actual file it's line number 31, but if you remove 1, 2, 3, 4, 5, 6 lines, it probably becomes 26, right? Yeah, so if you ignore the blank lines, this is line number 26. So it did not know what 11 was, but it went ahead and did everything. This is only a warning, it's not an error. Okay, so let's remove that. Save it. It's finished running, I think. Now that error, the warning message is gone. Okay. Okay, now we're going to switch to symmetric airfoils because that's easier to understand in the beginning, the early stages. And your first project is on symmetric airfoils. So we'll talk about symmetric airfoils, and then we'll go to the little bit more complicated case of cambered airfoils. So in a symmetric airfoil, so the sim keyword is needed because this is what tells profile that you're designing a symmetric airfoil. So all these things I'll give you templates. Okay, my template for the symmetric airfoil project will already have the sim, so you don't have to worry about that part. But just so you know what these things are, I'm telling you what is needed. So in a symmetric airfoil, upper surface and lower surface are mirror images, right? So your symmetric airfoil is going to look like this, something like this. And the circle in the circle coordinate, because of symmetry, you should have the I leading edge or the aerodynamic leading edge here. The I leading edge keyword should point to this. So let's say you have 3 segments on the upper surface, right? 1, 2, and 3. You have to have the same segments on the lower surface and they have to be mirror images. So your fourth segment should be here, fifth segment should be here, and sixth segment is always the last one. And everything has to be mirror image. So if this is alpha star of 7, this segment has to be alpha star of 7. If this is alpha star of 5, this has to be alpha star of 5. And if this is alpha star of, usually it will go up, so let's call this 9 and 11. Then this will be alpha star of 11. Like that, if this is phi of, let's say 10, then this should be phi of what? 50, right? Because this is 60. So if this is 10 this way, then this has to be 10 this way, so this has to be 50. And like that, so if this is phi of 24 something, so this will be phi of 36. And this will necessarily be phi equals 30 because the symmetric airfoil will have to be exactly divided. So think about this. This is going to be a pain, right? Every time you change this, you have to remember to go and change this. So you will say foil something here, then foil 24, 9. Then this will have to be foil 36, 11 because you're talking about this segment. But this, right? So anytime you change anything on the upper surface, you'll have to remember to go and change it on the lower surface. And that's a real bother. But fortunately, Profoil has been written so that you don't have to do that. And then that's the nice thing when codes are written by people who are using those codes every day, like not every day, but in day to day a lot. So if I write a code like this and I have to always go and put all these numbers, mirror image it and put it here, after the 5th time I'm going to get so bored that I'll go change my code to automatically mirror it, right? That's what happens with Profoil, with Xfoil. All these codes are used by the people who have written it. So what it does is, for symmetric airfoil, so let's see an example symmetric airfoil file. Here is a 4-segment symmetric airfoil demo file, which we haven't really used yet, but we're going to use it shortly. So this has got only 2 foil lines because ILE is 2. This is a 4-segment airfoil, right? So second segment endpoint is the leading edge, and that is ILE. And that phi, so you only have to give 2 segments. Profoil will automatically mirror it to create the lower surface, because that's a pain to do manually, right? You have to think, okay, if this is 14.5, then you have to say, okay, 60 minus 14.5, then you have to put all those foil lines. Profoil eliminates that kind of boring work for the user. And so remember, or note also that ILE is 30. So this is, remember, this is a 4-segment airfoil. What I gave in the example in this illustration is a 6-segment airfoil. So here, how many I'll continue this on the next page. How many foil lines will it have? How will this look? We have 2 minutes, so let's go through it quickly. It'll have 3 foil lines. So you'll say foil, can you see this? So foil 10, 7, 10.07, and then foil 24, 9, and then foil 30, this has to be 30, and this will be 11, right? What you might have had to do if Profoil didn't have the capability is you would have had to do foil 36, 11, foil 55 or 9, yeah, this is 9, and foil 67, right? These are automatically done inside Profoil. And so you don't have to write them, but then you also have to put ILE 3. Right, so these don't have to be, if you put them there's nothing wrong, but you don't have to put them. Even if they are there, Profoil just will ignore it. Okay, we'll stop here, we'll resume in the next class.